Good morning, I'm Loredana Caruccio from University of Salerno, and I worked together with Bernardo Breve, Stefano Cirillo, Vincenzo De Eufemia, and Giuseppe Polese on the definition of the tool DEVIS, which tackles with the problem of visualizing dependencies during incremental discovery processes. This is the outline of the presentation, and in particular, after a brief introduction to the data profiling and the definition of relaxed functional dependency, we will focus on the presentation of the proposed tool DEVIS by describing its architecture, its visual interface, and on how users can interact with it. Finally, we describe the evaluation performed through a case study, in which we focused on the dependency discovered from streams of data associated to the tweets post of the Twitter social network. So, let's start with our context, which is the data profiling. It represents the set of activities and processes useful to determine metadata about a given dataset. Such activities permit to create useful information that can be exploited into several application contexts, such as data cleaning and query optimization. There is a big number of data profiling activities, starting from the analysis of domain cardinalities to the discovery of functional dependencies and inclusion dependencies. In this proposal, we will focus on functional dependencies and relaxed functional dependencies. Let me now briefly recall the concept of functional dependency. It states that given two sets of attributes x and y of a relational database schema R, we can say that x implies y if and only if for every type of pair T1 and T2 into the database instances, whenever T1 and T2 are equal on the attributes in X, then they must be equals also on the attributes in Y. Here, a typical example of functional dependency defined on a database of people is that the city and the address imply the zip code. However, in order to identify data inconsistencies and pursue robustness with respect to data errors, in the literature many extensions of the canonical definition of functional dependency have been provided, and they have been generalized under the concept of relaxed functional dependency. In particular, RFDs relax some constraints of the canonical definition of functional dependency by admitting the possibility for a functional dependency to hold on a subset of data, and or by relying on approximate paradigms to compare pairs of tuples, and finally, by admitting the possibility of comparing attributes of different database schemas. This is the general definition of relaxed functional dependencies. It admits the possibility to limit the applicability of the dependency through a constraint domain DC. Moreover, it uses sets of similarity difference constraints to compare tuples in terms of similarity or difference values, operators, and thresholds. And finally, it can also consider a coverage measure psi, which permits to measure the satisfiability degree of the dependency, whose limit is defined by the threshold epsilon. This example, defined over the aforementioned context, can clarify the necessity to consider relaxed functional dependencies. In fact, starting from the canonical functional dependency city and address imply the zip code, in general, we should admit that tuples have been stored by using different abbreviations. here in the case of city and address. Thus, we need to admit a tuple comparison based on similarity rather than the equalities. Finally, sometimes we need to admit exceptions in the satisfiability of the dependency. In fact, for cities with very long streets, it could happen that the street has associated different zip codes. Thus, by using a coverage measure, we can handle the fact that the dependency is still valid even if there exists a portion of tuples violating it. Relaxed functional dependencies in general can be specified at the same time, but due to the necessity to define similarity thresholds and the satisfiability threshold, then defining relaxed functional dependencies at the same time results as a complex task. Thus, it is desirable to have means to automatically discover them from data. In the literature, several efficient algorithms for discovering RFDs have been defined. Moreover, recent proposals deal with the incremental or continuous data profiling scenarios, in which dependencies are updated after the insertion of new tuples in the data, as in this example. So we particularly focus on such kind of scenarios, which enable us to discover RFDs also from data streams. In the context of continuous profiling, the possibility to have a huge quantity of holding RFDs at each point in time yields the necessity to graphically visualize them. Indeed, a proper analysis of how RFDs change over time cannot be accomplished by looking at resulting RFDs over millions of time instants. To this end, we present DEVIS, which is a tool for analyzing and comparing RFD discovery results. In general, DEVIS enables the user to visualize the trend related to the number of holding RFDs over time, by also admitting the possibility to analyze the details of the discovered RFDs. Moreover, it enables the comparison of holding RFDs at different time slots. And finally, it admits the user interaction with the discovery results. DEVIS has been designed aiming to enable users to monitor results during the execution of RFD discovery algorithms through a responsive visual interface. Moreover, it is based on a client-server architecture, whereas each of its modules is a standalone and shares information with other modules by using the JSON standard. More specifically, the client is a web application that communicates with the backend modules through live queries. Instead, the backend server is a long-lived Node.js application running distributed jobs while keeping a live connection with the database. In particular, the backend modules receive data from live queries, process and represent them on the DEVIS dashboard. These are some of the components of the DEVIS dashboard. In particular, one of the main components is the line plot, which is responsible to display information about the number of valid dependencies discovered over time. It is divided into sections The upper one is the main line plot, showing the number of RFDs holding at each timestamp, whereas the line plot at the bottom is a replica of the previous one, but it enables users to select a specific interval of time through a brush. Moreover, Davis contains several statistical counters displaying the number of RFDs that are valid, invariant, and minimal on a given time instant, and some other counters showing the number of dependencies grouped by each right-hand side attribute appearing in the discovered RFDs. In this figure, we can notice one of the other main components of Davis, which is the dependency table, where each row represents an RFD and each column represents an attribute of the dataset, even if only the first column Only this first column indicates the attribute defining the right-hand side of the dependency. Moreover, one of the main features of Davis is the possibility to monitor the variation of the discovery results into two different time intervals. In particular, a dedicated button on Davis dashboard enables the duplication of both the line plot and the dependency table. As said before, Davis enables users to interact with its visual components. For instance, in the dependency table, users can reduce its contents by using two filters that are a global search filter, this one, and a column-based filter, this one. Moreover, there is the possibility to hide or show one or more columns into the table. Finally, there is also a paging functionality enabling users to decide how many RFDs should be displayed in a single table page. Referring to the dependency table interactions, we planned a particular behavior in the case of user decides to filter out the dependencies according to a specific attribute for the right-hand side. In fact, in this case, the filtering also affects the line plot, presenting a new blue line which shows information about the number of dependencies having that attribute on their right-hand side, and by showing how this number changes. Concerning the evaluation, we analyzed the effectiveness of Davis on a real-world scenario by analyzing discovery results on the data stream of Twitter. In particular, tests have been performed by considering 4 execution sessions, named A, B, C, and D, by using an incremental FD discovery algorithm, where each session lasting about 4 hours. Moreover, we considered 11 attributes concerning tweets account details, and we filtered tweets by considering only those containing 4 specific keywords. In particular, to get some knowledge on the FD validation trend, Davis enabled us to analyze line plots, As expected, the plots present an arc variation at the beginning of the sessions, and then they tend to be stable. In general, we can notice that the trends present several differences, especially for the first hour of the execution. Instead, by analyzing the number of discovered FDs at the end of the several sessions, we can notice that such number is quite similar. And in particular, according to the table shown on the left, this one, the different sessions shared many FDs. This results is not obvious, since in the most cases the tweets of the sessions are created by different accounts. On the right, there are some examples of FDs shared among sessions. In particular, the shared FDs provided us useful insights. For instance, by comparing the last two FDs, we can deduce that the number of likes named number of favorites changes more frequently with respect to the number of lists to which the account owner is registered. In fact, the number of favorites required another attribute. It has the attribute lang on the left-hand side of the dependency in order to be determined. So, by concluding, we presented a visual analytic tool named Davis, which allows for the interpretation of discovered dependencies over time. It contains several visual components, enabling users to actively analyze the evolution of holding RFDs discovered through an incremental discovery algorithm. In the future, we would like to define new visual components, for instance, for highlighting the stability of the dependency over time, and define new visual metaphors to graphically represent and summarize the general evolution of all holding RFDs. So, thank you for your attention.